Throughout the course, we're going to learn how to use Nmap in detail to scan the networks. Nmap, Network Mapper, is a free and open source utility for network discovery and security auditing. Many systems and network administrators also find it useful for tasks such as network inventory, managing service upgrade schedules, and monitoring host or service uptime. Nmap runs on all major computer operating systems, and official binary packages are available for Linux, Windows, and Mac OS X. Nmap has been used to scan huge networks of literally hundreds of thousands of machines. Nmap is usually very good at documentation. Significant effort has been put into comprehensive and up-to-date man pages, white papers, tutorials, and even a whole book. You can visit nmap.org to find out more about Nmap. While Nmap comes with no warranty, it is well supported by a vibrant community of developers and users. It's one of the most well-known tools of the network security domain, and indeed, with a lot of facilities, it's very powerful. In addition to the classic command line Nmap executable, the Nmap suite includes an advanced GUI and results viewer, Nmap, a flexible data transfer, redirection, and debugging tool, NCAT, a utility for comparing scan results, NDiff, and a packet generation and response analysis tool, NPing. Nmap uses raw IP packets in novel ways to determine what hosts are available on the network, which ports of these hosts are accessible, what services those hosts are offering, what operating systems are running, what type of packet, filters, firewalls are in use, and dozens of other characteristics. Beyond all this, Nmap has its own scripting engine and allows developers to develop new modules. In the following lectures, to discover the network, we'll perform the following with Nmap. First, we'll use ping scan to find out the hosts in the network. Then we'll use different types of port scan to find the open or accessible ports. We'll detect the services running on the ports and their versions. We'll try to learn the operating systems running on the systems. And after that, we'll see how to use scripts with Nmap scans. And we'll learn some important scripts as well. Nmap sends some packets to discover the network. To prevent security devices from blocking our packets, here's where we're going to learn some timing tricks. Then we'll see what we can do more of to bypass security devices such as packet filters, IDS, or IPS. Here, there's an Nmap command example. Let's see some basic parameters of the Nmap command. Nmap is, of course, the command itself. S is to define the scan type. If you use S with uppercase T, as seen in the slide, it means you want to run a TCP scan. We'll see the important scan types in detail. If you don't use this parameter and you have the administrator privileges on the computer where you're using Nmap, SynScan is a default scan type. If you don't have the admin privileges on the computer, TCP scan will run. Destination IP address is the only required parameter to run this command. It means you can run the Nmap command like nmap 172.16.99.139. This is the IP address of the target machine which you want to scan. You can either give a single IP address or give an IP block or an IP range as a target, but we'll see that soon. Destination ports are the port numbers that you want to scan. If the target port numbers are not given to the command, top 1,000 ports will be scanned. Be careful, I didn't say the first 1,000 ports. I said the top 1,000 ports. That means the most used 1,000 ports will be scanned. There are different ways to enter destination ports, and we'll see them in detail. I don't want to spend too much time on theoretical information, but to understand the packets sent to the destination systems and the reply packets as well, we should talk about the TCP/IP Internet Protocol Suite. OSI, Open Systems Interconnection, is a reference model for how applications can communicate over a network. A reference model is a conceptual framework for understanding relationships. The purpose of the OSI reference model is to guide vendors and developers so that the digital communication products and software programs they create will interoperate and to facilitate clear comparisons among communications tools. Most vendors involved in the telecommunications make an attempt to describe their products and services in relation to the OSI model. And although useful for guiding discussion and evaluation, OSI is rarely actually implemented, as few network products or standard tools keep all related functions together in well-defined layers as related to the model. Developed by representatives of major computer and telecommunication companies beginning in 1983, OSI was originally intended to be a detailed specification of actual interfaces. Instead, the committee decided to establish a common reference model for which others could then develop detailed interfaces, which in turn could become standards. OSI was officially adopted as the international standard by the International Organization of Standards, ISO. So what about the OSI layers? The main concept of OSI is that the process of communication between two endpoints in a telecommunication network can be divided into 7 distinct groups of related functions, or layers. Each communicating user or program is at a computer that can provide those 7 layers of function. So, in a given message between users, there will be a flow of data down through the layers in the source computer, across the network, and then up through the layers in the receiving computer. The 7 layers of function are provided by a combination of applications, operating systems, network card device drivers, and networking hardware that enable a system to put a signal on a network cable or out over Wi-Fi or any other wireless protocol. The 7 open systems interconnection layers are: Layer 7, the application layer. This is a layer at which communication partners are identified. Is there someone to talk to? Network capacity is assessed. Will the network let me talk to them right now? And that creates a thing to send or opens the thing received. Please note that this layer is not the application itself. It is the set of services an application should be able to make use of directly, although some applications may perform application layer functions. Layer 6, the presentation layer. This layer is usually part of an operating system and converts incoming and outgoing data from one presentation format to another. For example, from clear text to encrypted text at one end and back to clear text at the other. Layer 5, the session layer. This layer sets up, coordinates, and terminates conversations. Services include authentication and reconnection after an interruption. On the Internet, Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, provide these services for most applications. Layer 4, the transport layer. This layer manages packetization of data, then the delivery of the packets, including checking for errors in the data once it arrives. On the Internet, TCP and UDP provide these services for most applications as well. Layer 3, the network layer. This layer handles the addressing and routing of the data, sending it in the right direction to the right destination on outgoing transmissions, and receiving incoming transmissions at the packet level. IP is the network layer for the Internet. Layer 2, the data link layer. This layer sets up links across the physical network, putting packets into network frames. This layer has 2 sublayers, the logical link control layer and the media access control layer. Ethernet is the main data link layer in use. Layer 1, the physical layer. This layer conveys the bit stream through the network at the electrical, optical, or radio level. It provides the hardware means of sending and receiving data on a carrier network. Let's see some of the most famous protocols of the layers. For ease of use, it's better to talk about physical layer and data link layer together. Here we have some protocols in data link layer and some physical media and connection methodologies in physical layer. Ethernet and 802.11 wireless LAN are the most known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. You need to have network interface cards in the devices that you want to connect to the network. A wireless local area network, WLAN, is a wireless computer network protocol that links two or more devices using wireless communication within a limited area, such as a home, school, computer laboratory, or office building. This gives users the ability to move around with a local coverage area and yet still be connected to the network. Most modern WLANs are based on IEEE 802.11 standards and are marketed under the Wi-Fi brand name. IP, Internet Protocol, is responsible for addressing hosts, encapsulating data into transferred packets, and routing packets from a source host to a destination host across one or more IP networks. The best-known transport protocol is the Transmission Control Protocol, or TCP. It's used for connection-oriented transmissions, whereas the connectionless User Datagram Protocol, UDP, is used for simpler messaging transmissions. We're going to talk more in depth about these protocols in the next lecture. Again, for ease of use, the last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. Let me put another parenthesis here. We're talking about the OSI reference model here. In addition, there is another reference model called TCP/IP reference model. And instead of OSI model's last three layers, there is only a single application layer in the TCP/IP reference model. Just keep that in the back of your mind. And back to our subject. The application layer protocols are classified according to the protocol they are using in the transport layer. And these protocols interact with the end user via applications. Therefore, they are the most known protocols by just about everybody. Some of the most well-known TCP-based application layer protocols are HTTP, Hypertext Transfer Protocol, simply a communications protocol used to send and receive web pages and files on the Internet. Telnet is one of the simplest ways to exchange data between two computers. It allows two computers anywhere on a computer network, including the worldwide Internet, to exchange text and, other data in real time. FTP, File Transfer Protocol, is a communication protocol for the rapid, simple transmission of files across a network. SMTP, Simple Mail Transfer Protocol, is used to send and relay an email message between email servers. Note that it is not used to retrieve email messages from a server. Instead, either IMAP or POP is used to retrieve email messages. DNS, the Domain Name System, is a system used to convert a computer's host name into an IP address on the Internet. For example, if a computer needs to communicate with a web server nhs.uk, your computer needs the IP address of the web server nhs.uk. It is the job of the DNS to convert the host name to the IP address of the web server. The DNS uses both the UDP and TCP. SNMP, Simple Network Management Protocol, is used in network management systems to monitor status of devices and also spot problems. So let's see what happens to a packet inside the network traffic. Please note, the data unit transferred between two endpoints has different names in each layer. In layers 5, 6, and 7, application layers, it's called data. In layer 4, transport layer, it's called segment for TCP and datagram for UDP. In layer 3, the network layer, it's called packet. In layer 2, the data link layer, the data unit is called frame. Now, I usually use packet for the transferred data unit in each layer to make it less complicated for you. Make sense? Before looking at the road trip of a DNS query in detail, let's look at the relationship between the OSI layers and computer systems. The packets in Layer 1 and Layer 2 are managed by network interfaces of your device, for example, by your Ethernet card. And the packets from 3 to 7 are managed by the processing unit. In software detail, the Layer 3 and Layer 4 packets are managed by the operating system of your devices. And the packets of Layer 5 to 7 are managed by the related application or service, for example, a web browser. When you write a URL in the address bar of your browser and hit Enter, the first thing it sends is a DNS query. A DNS query is the process of a computer or networking device making an inquiry to get an IP address for a DNS name such as mail.yahoo.com. The client computer will send a DNS query to one of their Internet Service Provider's DNS servers. The DNS server looks in its DNS database to tell whether it can answer the query authoritatively. If the DNS server can answer authoritatively, the DNS server answers the query and the DNS query process is complete. So let's see the road trip of a DNS query from your computer to a DNS server. When data is transmitted by the source toward a specific destination, it passes through the application, presentation, and session layers, and the protocol data unit arrives at the transport layer, Layer 4. Layers 5, 6, and 7 are displayed as a single layer to simplify the presentation. At this layer, a 20-byte data header is placed in front of the data. A DNS query can also use TCP, but let's assume that it uses UDP at this time. The data and the Layer 4 header, here it's UDP header, which together form a segment or datagram, is passed down to Layer 3, the network layer. The network layer places its Layer 3 header, here the IP header, in front of the received segment, and this group becomes a packet. The Layer 3 header contains important fields such as the logical address, the IP address, of both the source and the destination device. The newly formed packet is then passed down to Layer 2. The data link layer creates a new data unit called a frame by adding the Layer 2 frame header, which is the Ethernet header here. Like Layer 3, an addressing structure is also applied in the Layer 2 header. That is, the MAC address. The frame is then passed down to the physical layer, which converts the information into 0 and 1 bits that are sent over the physical media using electrical signals, on a copper link, for instance. Finally, the data is sent over the wire using a wide variety of methods such as Ethernet or token ring. The headers are a specific form of control information that allows the data to go through the network properly. Thus, the data at each layer is encapsulated in the information appropriate for the specific layer, including addressing and error checking. The overall size of the information increases as the data travels through the lower layers from Layer 4 to Layer 1. The destination device, which is the DNS server here, receives the data, and this additional information is analyzed and then is removed as the data passes through the higher layers up to the application layer, where the data is decapsulated. The physical address, commonly the MAC address, which is located in a special field in the data link layer header, changes as the packet passes from one device to another. For example, from the source PC to a switch to a router to another switch and finally to the destination PC. However, the original IP source and destination addresses do not change when transiting the network because the packet is stripped of its Layer 3 header only when it goes beyond a router. When it stays within the same LAN, it only passes through switches which decapsulate it at the Layer 2 header containing the MAC address. As a result, the header changes as the packet is re-encapsulated, as does the MAC address fields. The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet Protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, And because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. Okay, now we can continue to talk about TCP's three-way handshake. Step 1. Computer A sends a SYN data packet to computer B. SYN data packet means the data packet where the SYN flag of the TCP header is set. Wow, what does setting the SYN flag mean? That means making the SYN bit 1. The objective of this packet is to ask if computer B is open for new connections. Computer B must have open ports that can accept and initiate new connections. Step 2. When computer B receives a SYN packet from computer A, it responds and returns a confirmation receipt, the SYN ACK packet. As you understand, SYN ACK packet means the packet in which the SYN and ACK flags are set. Step 3. Computer A receives the SYN ACK from computer B and responds with an ACK packet. At this point, both computers have received an acknowledgement of the connection. With these, a full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss tolerating connections between applications on the Internet. TCP has emerged as the dominant protocol used for the bulk of Internet connectivity owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead, and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol.